All right. Well, while everyone starts to kind of settle in, I will go ahead and do the introduction. Hello, everyone. My name's Adrian Edge, Director of Codes and Regulatory Affairs here at Fenestration Canada. Terry has kindly given me the reins to go ahead and run this show with Anton. Um, Before we get started, I want to give a big thanks to our sponsor for this, OpenJanela. So, for any of the manufacturers that have gone through ERP work or you have flirted with the concept of ERP work, you will appreciate how challenging it is to integrate into an ERP. Specifically, fenestration industry being a round peg and many of the ERP systems being a bit of a square hole to shove it into. Um, One of the benefits of OpenJanela is that it is built for the fenestration industry. So a lot of the best practices that we would view in running a fenestration manufacturing side is already built in. So yeah, again, big thank you to OpenJanela for sponsoring this as for all of our tech talks this year. And then I'm going to do a very brief introduction to Anton van Dyke. For most of you, you will know who he is, so I don't have to actually do a whole lot with him. But Anton works with JRS, specifically with fenestration. He's been in our market for a good long while, and I will give you most of the reins to introduce yourself, Anton, as I kind of like to do the same. But just as a note, at the end of the presentation, we're going to give a poll if the attendees don't mind. It'll be about this topic and how important you feel it is to the fenestration industry. It would be really helpful for you to answer it so that we just kind of get a feel from our audience what you would like to see from this topic moving forward. So, Anton, with that, I'm handing you the reins. All you.
Thanks, everybody. I think I see the list, and most of people on the list, I think we've interacted. Bit of background just on myself. For those of you that don't know, JRS Engineering was where I started my career in leaky condos in Vancouver back in the late 90s. I was a 21-year-old kid climbing up ladders, poking holes in buildings, and figuring out what was going wrong with buildings. And so when we get into this topic of durability, I find that background that I just sent in a request to share my screen. I find the background and the concept of durability a very, very interesting conversation, because if you talk to anybody who's worked in Vancouver for the last 20, 30 years, we had a very, very big problem with durability. And we had buildings fail within 2 or 3 years. So that was we defined what durability is very quickly when it came to building envelope. And then back in about 2011, I took that concept into fenestration, and now, a couple of years ago, decided to kind of pull back and go into the consulting side with the idea of really connecting the dots between the specifier and the manufacturer. And I think that's the important conversation here. Is we have designers, architects, engineers, specifiers, that world. And we don't always sort of connect the dots between manufacturer and specifier. And I think, when I talk to specifiers, architects, and engineers, and I say, how do you go about determining what's appropriate for the windows that you design into your project? And he goes, well, I draw the window and I hope the window manufacturer tells me the limit of their product. And I go, when do you ask for that? Well, I hope they're going to reach out to me. And I'm like, well, okay, is that working? How do you call them? How do you communicate with them? And I was used to say the best question that I used to get as a window manufacturer from an architect, they'd call up and go, what's the biggest window you could make? And I'd say as big as I could put it on the back of a truck before it hits a highway overpass. Doesn't mean it's going to work. And it was kind of a tongue-in-cheek comment, but it kind of made people think about, like, oh, we have to really consider these, what, Adrian and I have talked about, the 17 things that a window has to meet on a building. And so durability, to some people, aluminum glass will last forever. So that's durable, but does it perform correctly? So with this presentation that I've put together, it is a presentation that I gave a couple weeks ago at the BC Building Envelope Council AGM, which is basically everybody from Western Canada in the building envelope community, architects, building envelope consultants, engineers, specifiers that come out, everything from roofing to windows, anything building envelope focused. And the topic was about climate adaptability for the future, and looking at what do we have to prepare for into the future? Could we look at the past to gauge what we're going to do into the future, and how does this factor into durability? So it really gets into this sort of nuance of what we're seeing. And so I'm going to dive right into it. So I like to start with a history lesson, and in regards to building envelope and building science and what we learned in British Columbia over the past 30 years. So, we get into this world of what we call leaky condos, and this is going to be a fairly heavy BC focused, Western Canada focused presentation, just based on the audience I sort of gave it to, but it's going to apply for the rest of the country if you can kind of look at it. But I have two types of buildings. Building number one on the left is a mid 70s, early 70s stucco wood siding building. This photo is about 2 years old. It's been this way for a long, long time. No one's ever upgraded it. It's always been fine. And the building on the right is a building from the 80s, mid 80s, late 80s that basically within 2 or 3 years failed. We had to take all the cladding off of it, replace everything, put new windows and new balconies. This is sort of the transition of why did we not have leaky condos in older buildings, but we had leaky condos in newer buildings kind of going into the 80s and 90s. And what happened is in 1978, we had this thing called the Measures of Energy Conservation in New Buildings, which basically started looking at buildings saying, hey, we need to make them more energy efficient. Does that sound familiar? Does that sound like what's coming to our codes today? In BC, we have the energy step code, the national code has got the tier code coming. But there's a similar transition happening where we're looking at making walls more energy efficient. We're putting more insulation in them, which in essence is changing the way that the walls perform. And so what happens is these two buildings are within probably 3 or 4 blocks from each other. So they're in the same climate zone. And building on the left is basically got, well, bad systems, but there's so much energy flowing through the walls that its drying potential is higher than the wetting potential. Once we added more insulation, put poly in the wall, we essentially increased the wetting potential of the wall or decreased the drying potential. So the wetting potentials are the same. And so this is the idea of how simple a code change can happen that can then have an unintended consequence that we may not be paying attention to. And I bring this up because we've had energy codes now in BC for probably 5 or 6 years now that have changed how we insulate walls and deal with air barriers, moisture barriers, that sort of thing. But the new topic that everybody's talking about is embodied carbon. And when I talk to certain influencers in the world of reducing embodied carbon, my cautionary statement is could it have an impact on increasing or decreasing durability and making a decision that is on a durability scale that we have to focus on. So the whole purpose of this slide is to recognize the idea that one change somewhere can have a ripple effect down the road that we may not be paying attention to. So the history and evolution of windows, looking at wood windows in buildings from the 50s, then you get into the 60s and 70s where aluminum starts to come in, and you can see the transition of a window goes from from a functionality perspective. Mullion thickness was based on operator balanced weights to then getting into aluminum where you can get thinner frames. And then we move forward to today where we have situations where windows have just gotten bigger. The window to wall ratio has never been as extreme as it has been in today's design. And we've got energy codes that are looking at lower conductive building materials in the building, which generally go to synthetics and plastics. We're moving away from the stiffer products, the more durable products. And our windows have basically become an architectural feature, not a simple aspect of function. And that's where I sort of start to dive into the idea of now they're architectural. So there's a whole new level of influence that an architect is having on the product that you're supplying and providing for a building. And it's triggering sort of interesting, unique conversations. So looking at BC, and this is sort of from the rest of the country, from the tier code, and I'm going to use a sort of a part 3 multifamily kind of wood frame building concept here. When we look at the step codes of what we have in British Columbia, we're hovering around between step 2, 3, and 4. And why it's a range is code minimum. In British Columbia for multifamily buildings is going to be step 2. Step 3 is the most commonly seen step that I would see in the actual specifications that we see today, and some in step 4. And the reason why we see a variable aspect here is it's municipally driven. Certain municipalities will adopt a higher than code minimum step code, depending on their perspective of climate resiliency that they want to put into. And it's also tied to zoning. So you get situations where if somebody takes a lot and they want to upzone it so they can get higher density, the municipality might say, well, you can, but it needs to be step 4. I've also seen projects where CMHC has come in and said, we'll provide you funding to build this rental building, but it must be step 4, not code minimum step 2. It changes the dynamic. And So what happens here is my traditional presentation I do for architects is I'll always ask the question, what is the U value in solar heat gain that you will find in this range? And now I just added durability because I think this is the next conversation that we need to start having. And so what type of products fall into this range? And a really important conversation that I've had with manufacturers is, as these red lines move up, do you think the products that fall in that range start to change? And it's no different than governments mandating that we all drive electric cars, or they mandate fuel efficiency regulations in cars. The car you used to drive in the 70s, you do not drive today. And that's done through miles per gallon fuel regulations that have come in, basically saying this is the cap, this is the limit. And we're not seeing the, mandated you must use this type of window like they've tried to do with cars, but we're seeing them mandate the energy efficiency aspect. Next, you're going to see the mandates come into EPDs. You can't put a product with this much carbon in a building. I can foresee that into the future, which is going to start to, okay, what does that mean for the product? Do I have to take the steel reinforcing out of my product because steel has higher carbon than an unreinforced vinyl window? What does that do for your NAFS rating? So this is where you see, I did that LinkedIn kind of post a while ago that I find a window has to meet 17 criteria. Could there ever be a conflict? And we're facing massive conflict in regards to how do we strip out carbon without reducing durability? But how do we define durability? Is deflecting greater than L over 175 a durability conversation? Does it reduce the performance of glass over time? Those are the kind of conversations that we need to start having. So, if you're used to making sliding windows and you can make them very efficient, very fast, very cost effectively, well, once you start getting into the upper ranges into this category, it's harder and harder to hit the U values of a sliding product. And so those products start to become more and more obsolete. We see this with a lot of doors, where door products are falling off the list that the consumer wants to buy. And I think I always link that to the car industry, whereas the type of car that the consumer wants to buy doesn't always match the regulations that the government is putting upon society. So it's important we start having these conversations and ask the question, and predictability. Can you predict what products are going to be demanded 5 years from now, 10 years from now? Because if you're going to go into an R&D phase and redevelop product, you're not developing it for today. You're developing it for relevancy for the next decade. And so this is the interesting conversations. And what's changed from probably 20 years ago is the rate of change. Change has always been in front of our industry, but the rate at which it's changed is at a pace that we're not typically used to. So getting into sort of energy calculations and where we go with this, energy modeling, whole building solution. So if you've ever worked with an energy modeler on a project, you'll start to realize that they're dictating specific components that go into a building, in particular to hit the thermal energy demand intensity, which starts to define higher performance windows that go into it. So this is where you're starting to see the influence on why are certain types of windows being specified on a building from an energy perspective. It's the energy advisor. It's often done very, very early on a project at the zoning stage. So you have, as a manufacturer, very little input and ability to provide feedback to design teams about what can or cannot be done. And this is why in my view, companies need to put a high level of effort into business development, not from selling, what a product looks like, but from a perspective of meeting with architects to update their understanding of specifications. If you go back 25, 30 years ago, before Google, every architect had a spec library. They typically had a spec writer, and product manufacturers had technical representatives that went door to door into these architects' offices and updated the binders and updated them on what was new about their product and what they're doing. And you had face-to-face communication. That culture's gone in our industry. Architects simply Google. And I hate to say it, when you look at Google and AI, it pops up, yep, we have a solution for you. Okay, go design it. But the background research that needs to be done, and this is where I get into this idea of how would you define the term high performance? And I actually hate this term. I think this term needs to be stopped being used across our industry because, in my opinion, how high is high? What is the limit on it, right? What is big? Is a dog big to a mouse? But what about a dog to an elephant, right? The relevancy and context here is really important. And there's a really cool context exercise I've done in the past. And I asked the question, what's the best fruit? If you ask an audience of 50 people what the best fruit is, you're going to get a lot of different answers and arguments back and forth forever. But if you ask what fruit provides the most vitamin C, you're going to get very narrow focused answers on this. And so I did a presentation a few years back and I asked the audience of engineers and architects, what's your definition of a high performance answer? And I kid you not, one person said high solar heat gain and another person said low solar heat gain. So what is it? And my answer is, what's the right window? What's the right window for the right building, for the right design, for the right implementation, for the right goal and the right expectation? And so we got to start getting into this idea that high performance windows is not necessarily a solution, because some people are going to start pegging low carbon embodied carbon windows as high performance windows. But on a, let's take a 20-story high rise with high wind loads, is that appropriate? Could that be appropriate? And what does that look like? So we have to look at it in a world of context. And I did a post a while back on LinkedIn, and I got this really cool comment back from somebody in regards to energy codes. And it talks about the focus of total energy use as a target for design and construction. That is basically the definition of energy codes, energy step codes. Creates a significant number of less than optimal choices. It's acknowledging the fact that the products we're used to using today may not be relevant for the future. Knowing how much gas a truck uses in a year does little to understand what load it can carry up a hill and safely descend it. And if you've ever tried to tow a trailer through the Rockies, you'll know it's important what vehicle you have towing that from a safety perspective. And so there's a number of times you can drive through the Okanagan or the Coquihalla Highway here in BC, and you'll pass a pickup truck with a flipped over trailer on the back because it was basically not capable of doing it. So this is acknowledging this idea that total building energy codes does nothing to understand the products we put into certain components and what happens to its level of durability. So it might work for a calculation, right? So we've all seen this from solar heat gain. It works great in the calculations for total building energy efficiency, but it may not work for the component. So what's changing? What do we have to factor in? And being a born and raised BCer and growing up in this sort of region my entire life, I can assure you that in the last 5 years, we've seen events happen in British Columbia that we have never seen, that I've personally never experienced before in my entire life. And in the last 5 years. So key aspects, I took Victoria, average temperatures, highs and lows. So an average low of 3, Kamloops, an average low of 5. And then I get into the extremes. And in June of 2021, we had an interesting event. We called it the Heat Dome. We've attributed significant number of deaths that occurred as a result of this. It's triggered code changes. It's brought in ideas of like how to regulate temperatures in houses. And those of us in the window industry actually know you don't always have to put air conditioning in a home. You can actually deal with it with low solar heat gain glazing, which when I was hearing on the news, they were trying to codify air conditioning in buildings. I was always frustrated because there's more pragmatic solutions with glazing systems and shading. But, not everybody wants to react in that sort of perspective. So we had this situation where we saw up to 40 degrees in the lower mainland in Victoria. So these are oceanfront cities that generally have mild and temperate climates that don't swing that high. And so 40 degrees, and subsequently in the interior of British Columbia, we hit 50. So I was actually camping with my family in this range when it hit 50. So I personally got to experience 50 degrees. Not a fun temperature to experience when you're in a tent trailer with no air conditioning. Actually kind of scary. And then in November of that same year, we had this thing called an atmospheric river, catastrophic. We had fatalities as a result of it. We had more rain in one day than I think we'd ever seen in probably a month in that type of situation, which was catastrophic for our infrastructure. That was never designed to accommodate that. We're still rebuilding from it, by the way, in our highway systems as a result. And then just recently, January 2024, we saw temperatures dip. Some of you might laugh to us in BC about these temperatures going, this is normal for us. And so I think that's an interesting conversation, but this is not normal in certain climates like Vancouver. But if you get a minus 15 degree day in Vancouver, Victoria, the product you're used to putting in those buildings might not perform the same way it's used to. And similar in the interior, if you actually go to wine country in the interior of BC, the catastrophic kill off of grapevines that people have never seen before was huge. So I use this as an aspect of we have to acknowledge, 40 to 50 degrees Celsius temperature, minus 25 temperatures. We have this extreme now that we have to focus on. And in the middle of it, we're going to get heavy rainfall. So now we have all of these things happening in our environments that we have to pay attention to. So I'm going to bring up, this is Palm Springs. And I bring up Palm Springs because, and I'm going to show a slide here after that sort of connects the dots between it, but we are getting Southern California-like temperatures in Vancouver, which, in my entire lifetime, we've never experienced. So that's sort of a new thing, right? So this is the change that's upon us that's going to start to factor in durability and the things that we put into our buildings and how they're going to perform overall. And looking at it from a pragmatic, holistic, big picture aspect, not just a calculation that software tells us it's going to work. So examples of performance considerations linked to durability. So we're going to get into the guts here now of specific examples of what we're seeing today. These are actual real life situations that are occurring. They're from multiple projects. They're reflective of multiple products. It's not discriminatory towards any specific aspect of a manufacturer or anything. So I just want to sort of get that out there. We have to have this conversation. And architects, engineers, and specifiers who are becoming responsible for the material that they specify on a building need to become aware of the limits and the boundaries of that product based on the environments that it's being put in. And the best way to look at what works and doesn't is look backwards a little bit in the last 5 years to sort of say, in those extreme environments that the products have gone through, can we use that as an example of what we might face into the future? So first one I like to look at is excessive localized. And I'm going to amplify that, excessive localized air leakage in cold climates. High solar heat gain glazing damaging window frames. This is a bit of a regurgitation of a previous tech talk, so I got some content there. But a lot of architects and engineers are not aware of this issue. When I share the image that's from a previous tech talk with energy advisors on what a 0.4, 0.45 solar heat gain coefficient can do to a window, they're shocked. They have no idea that this is a possibility, which that's something to consider when we start interacting with designers. Dark window frames at peak summer temperatures. This is going to be a big part of the conversation. And this is because windows have become architectural versus functional in our sort of transition through the processes. And what happens when you put a dark color on a window frame? And what type of window frame is it? What is the color? What is the material? And what happens at 40 degrees Celsius is really the big question. I have two other topics I want to open up into conversation, but this thing's going to turn into 4 hours if I get down into this. But we need to start having more conversations about the use of Surface 4 low E in cold climates in lieu of triple glazing. What is the boundary? What is the limit of Surface 4 low E from a condensation perspective? That is a future conversation. There's too many designers in the industry, specifiers that are in the black and white on this. Don't do it or do it. I put it all in my house, because I was really frustrated with one designer out there who was trying to influence that Surface 4 low E should never be used. But in a mild climate, it has a very significant relevance. And in the conversation about embodied carbon, would a Surface 4 low E be better than triple glazing from a carbon conversation? I think so, because it's less glass. So, but in cold climates, we have to be careful. And that's where I see the common mistake made is, oh, we did that on a building in Vancouver, but then we do it on a building in Kamloops where we start seeing minus 25. So those are the kind of, we need to know what is the boundary. And there's actually tools that we can use now. Cardinal developed a chart and presented it. I remember seeing it like 15 years ago, I think, on how to determine center of glass condensation temperatures using different low E coatings to determine condensation. And then you use that with a psychometric chart. You do your dew point calculations, and you can predict condensation scientifically. Interestingly enough, I was reading a bunch of thermal modeling reports from Intertech yesterday, and they got a disclaimer about condensation resistance, being it's a simulation, not an actual result, and it doesn't factor in convection currents and airflow and all of these other things that you work with when it comes to condensation predictability. So I have a Surface 4 low E window right above my kitchen sink. I got a mid-70s house with poor ventilation on a crawl space that often gets wet. I got a high water table, so I generally have a high humidity in my home. I have a dishwasher right below it, so I have a very high humid scenario right below my Surface 4 low E window, and I get no condensation. And I'm just outside of Vancouver. So the real life scenarios don't always match the predictable calculations we do. And then low solar heat gain glazing reflectivity causing fires. This is one that I think no one is ever even considering. I've had, I think it was 3, maybe 4 now in the last 5 years where people have shared me photos of patio furniture catching on fire next door of a building because of reflectivity of glass And there's certain scenarios that happen. I know this is a conversation I think not necessarily linked to durability, but it's something that I think designers need to be aware of when it comes to different orientation, especially round and curved windows with when the glass has a bit of a concave effect to it. So first one, excessive localized air leakage at peak winter loads. So common issues with doors, and I'm really going to amplify the swing door industry issue, and something I learned when I transitioned a bit of work into the Calgary market, where you see sustained cold temperatures and French doors, and in some cases patio doors, is you may have a situation where your door tests and it meets an A3 air leakage level. Great. It meets A3, it's got an air leakage rating of less than 0.5. We're all good, except 80 to 90% of the air is leaking through one small location. And that's what I think most everybody looks at, the holistic performance aspect of the product. But what if all of the air leaked through the astragal at the bottom of a French door in this one location? For those of you in cold climates, you might probably already know the answer to this, is customers complain that they got ice buildup in certain locations of the door and the door won't open or close. So this is a similar kind of conversation about industry standards don't necessarily provide us with the understanding and the logic that could come with durability and the expectation of durability in that specific climate aspect. So not a huge important conversation to have, but it is something to pay attention to when you're selling a product from a mild climate into a more extreme colder climate. This is the Tech Talk image. I've always been meaning to talk to FenCam, see if, I don't know if this image is actually available, but I took a screenshot of the Tech Talk that was on this issue about melted windows and high solar heat gain. So there's a whole video on this, and in regards to this window and this scenario. And I use this example when I talk to energy advisors about the consequence of high solar heat gain and how that impacts it. And in every project that I could say that I've been involved with in the last year, that I've been working with in new construction, multifamily building. And I'll use an example. I have a project where there's limited electrical supply to the site. And it's in a jurisdiction that has adopted the carbon, with the zero carbon step code level. So there's a design criteria that the building is not allowed to use a certain amount of natural gas. They're basically trying to eliminate natural gas for heating, but this building does not have sufficient electrical supply to heat the building completely with electric baseboard heaters. So it needs natural gas to heat the building. As a result of that, high solar heat gain windows were specified for free heat in the winter to offset the amount of carbon that would be burned to heat the building. And it was pushing into the 0.45 range. And I took this image. We had a meeting with the developer builder. It was the same kind of company, really big developer here in Vancouver. And I shared this image with them and I said, if you do this, this is a potential possibility. And within, not kidding you, 5-10 minutes, the developer said, lower the solar heat gain, we'll deal with the situation and the energy calculation. They were more concerned about this issue potential. And I was shocked at how quickly. And the feedback I started getting was developers who have been building in the last few years to the higher levels of the energy step code in BC are starting to get customer complaints about buildings overheating. And so they're recognizing the fact that the buildings they're building are not meeting their customers' intentions, the homeowner. And I think this is the conversation many of us don't have. If you sell windows to contractors, you have very little interaction with the end user of your product. But if you are selling replacement windows and you're sitting across the kitchen table from homeowners and you're taking old windows out and you're putting new windows in, I can assure you, when you have that conversation with the person who's interacting with your product, you're having a different conversation. And what people want in their home versus what a developer builder wants to buy, they're two very different things. And you can see it. I'll actually go back here. What I learned in the Calgary market is a lot of developers will put double outswing French doors in homes, and then 5 years later the homeowner will take it out because they don't like. Then they'll put a solid mullion in here. They'll do a fixed panel and only have a single operable. They won't use the French door because there's so much localized excessive air leakage with French doors in cold climates. They don't work. And so going back to this conversation and the story that I like about this one, and I'm going to kind of paraphrase it a bit because I don't know the exact, it's all second, third hand information, but it's this idea that, and I'm going to use it as a bit of I think it's just a story, that this home is built by a developer. It's built and sold and designed and sold as a high performance home. And let's say it's got solar panels on it. It's got extra insulation in it. It's in the upper levels of the step code. and it's got high solar heat gain. So the design might be 0.40 in the energy calculations, but most of you know, can you do a 0.40 solar heat gain window? No, you're probably selling a 0.45, a 0.48. In fact, some windows I've seen come through at about 0.52. So yeah, the energy advisor might have said 0.40 or higher, thinking or higher is okay because yeah, more heat in the winter, the better. What's wrong with that? From an energy calculation perspective. But the more heat coming through, is that okay for the window? And so what happens here is the homeowner moves in and the homeowner is like, hey, my air conditioning is on from May to October. This is odd. My home is overheating. I can't do it. They start looking at their energy bills in the summertime and they go, wow, we're consuming so much electricity for air conditioning. And then someone comes along and says, hey, we can sell you these heat reflective blinds that we can put on the inside. Or in my own personal case, my wife used to work the night shift in the ER and she'd come home at 7 in the morning and sleep from 7 till 1, 2 o'clock. And we'd have these blackout curtains with reflectivity on them so that it was pitch black in the bedroom. And so the point I'm trying to make here is to designers is, yeah, you can design high solar heat gain and you can say, oh, we'll put air conditioning in to deal with comfort. Fine. But what happens when somebody says, I don't want to pay these bills, or someone says, I want a blackout curtain, and they put something on the inside? We all know that we want shading on the outside. Those of us that have traveled through Europe will see every single home with external shading. But when a homeowner puts it on the inside, what happens with these heat reflective blinds is you create basically a zone here between the glass and the heat reflective blinds that's now getting up to a temperature where you're seeing vinyl reversion. Basically, the vinyl's replasticizing. It's going flexible. It's hitting a certain temperature at which it doesn't melt, it softens to the point where it changes its shape. And this is where the conversation needs to start, is what is the temperature at which PVC starts to change its shape to get into this sort of deformation scenario. So this tool, this information, this tech talk in the hands of energy advisors is eye-opening for the design community. And I'm quite shocked at it. And if you start bringing this conversation up more at that level, you will start seeing a shift in how solar heat gain is used in buildings and decided how to be used in buildings. So understanding how vinyl will change that shape, I think the important part is for designers, specifiers, they have no idea how products put together, how it's developed, how it's extruded. And it's this idea of the PVC polymer in its natural state versus when it goes through an extrusion and the polymers get stretched out and elongated and then it gets locked in place through the curing, like when it cools down. And it's this idea that the product and extrusion is always in this sort of tension. It's always wanting to pull back on itself. It's wanting to go back to its natural state, but it's locked in. It's unplasticized. It's rigid basically. And so what happens when you heat it up to a certain temperature, right? There's melting temperatures, there's softening temperatures, there's that, plasticization temperature that comes into it. And people will use terms like reversion, replasticizing, and go from there. And there's this table that I picked up on. It's heavily used in the design community, especially in the energy side. It's the ASHRAE Handbook of Fundamentals, and it's a chart that looks at light-colored surfaces versus dark-colored surfaces. So it's not about it's just about the surface of a material. It looks at the solar time of the day, so 5 a.m. to 20 hours, air temperature. So this is the ambient air temperature that it's exposed to, and the elevation of the product, and it looks at the heat gain from a light color to a dark color. Now, how dark? It doesn't really specify, so it's not necessarily giving you an idea. But when we start looking at, what happens to a dark colored surface at 12 noon, and we often think that south elevation at noon is the peak time when temperature gains are occurred on a building and when we get the maximum sort of heat gain occurring. But the sun's often in the summertime high in the sky. This is July 21 at the 40th latitude, which is about Northern California. But it looks at a 32.5-degree ambient temperature at noon. South elevation, you're looking at 50 degrees. I'll go to 4 o'clock. So the setting sun as another intense moment. And this is what I think the important part is, setting sun at our latitude might be more like 1800 hours because this is Northern California. So it's sort of giving us a ballpark. And I bring this up because this document's a tool that designers use to predict what could happen. And this is the important part I think everybody needs to be aware of. Designers will use whatever tool they have in front of them to predict what's appropriate when it starts to come into the definition of durability. So the more of the conversation we can have between industry and designer, the more we can start to understand the boundary conditions that we expect the product to go through and design product accordingly. And what you'll see here is at noon, the south elevation is 50 degrees. Yeah, hang on, no, back up here. So the south elevation is 50 degrees, but a horizontal surface is at 70 degrees, over 70 degrees at a 32.5 degree day. So that's sort of an indicator of how much heat gain is occurring on that dark surface on a flat surface. And the reason why it's the horizontal surface is because the angle of the sun is high in the sky and the intensity is at an extreme, versus the setting sun on the west elevation goes from 35 degrees ambient air temperature to a 70-degree temperature, versus the light colored surface where you're going, it's a 20-degree drop in temperature in the same exposure locations. So this is just a tool that designers are using and sharing it with everybody in regards to how do we predict what can happen at these temperatures. Now, what happened in BC is we started seeing 40-degree temperatures in the Vancouver region. In the interior, we started seeing 50. So this chart is at 32.5 and 35 degrees. So it caps out. So it's not giving us the full spectrum of what can happen, but we could probably plot this on a graph and use it to project what it could be. So what happens if at 35 degrees, we're hitting 70, at 40 degrees, could we be hitting 80? That's really the interesting conversation that we need to start having. So, because these environments are existing in our climate. So what happens to PVC when it nears 80 degrees? Well, we start seeing this type of action to it, where we see from the inside, we have a situation where high solar heat gain has caused this issue, but we're also seeing this kind of observation happening significantly in our climate zone right now. This looks like a white window, but it's actually a white vinyl window that's black on the outside. What a lot of engineering firms are doing, and it's really big in British Columbia, and it's driven by a lot of the warranty insurance aspects that we do because we had building envelope failures over the last number of years. So we have a warranty insurance criteria that's linked to certain timeframes, and the big one is a 5-year warranty component linked to water ingress. And so our firm, for example, will get hired by condominium owners and we'll come out and we'll do that 5-year warranty review. So just before the warranty is up, we go to the building, we go through it all. The interesting thing, and I've talked to a number of other firms, is every window that they've looked at that's dark, I don't want to say every, but a lot of windows that they've looked at that are dark that went through the heat dome, we're going to see a lot of the observations in the next photos, but the sashes look like this, right? So you can see an obvious bow that's going on here. And so what's going on? Like sometimes it's subtle. Some people aren't even picking up on it. And what you get is comments from people going, hey, my window's drafty, my window's leaking, my interior finishes aren't aligning with my window anymore. It's not necessarily linking everything together. And so what's happening here is you have a situation where the window's heating up on one side, but not the other side, right? So you've got a controlled condition on the inside, you got an uncontrolled condition on the outside, you're getting 40 to 50 degree ambient temperatures, it's heating up that one surface, that vinyl is reverting, it's going back, it's releasing the tension in that polymer, and it's causing it in essence to shrink, which then causes the sash to bow in this direction, which now results in this weather stripping in this location, losing compression and gasket seal. And this is where we start having the conversation about durability versus performance. And if we can start linking the concept of, is the window performing now for air tightness and water tightness as it was intended to do so once it goes through a heat event like we saw in June of 2021. And so going back to Palm Springs, this was me pulling up to an Airbnb in Palm Springs, a nice dark brown insert, kind of a piggyback window was put into this 1960s stucco building, dark frame. And sure enough, you're seeing this actual situation playing out in a climate zone where it's very common to see a 40 degrees Celsius summer day for sustained periods of time. And I think this is an important part about this situation is it's not about duration of impact. It's about, did it get exposed to that temperature, and how long can a product be exposed to that temperature is a sort of an interesting question to start sort of digging into. Is there a sustained sort of component to it? And so The next series of photos are going to be examples of what we're seeing when we do these reviews of existing buildings. This is the building that went through the heat dome, so windows were put in prior to June of 2021. And with the after that effect, we started seeing a situation where this is the hinge side of the casement sash. This is a cam push out window, and you can see the gasket compression on the leading edge versus the hinge side is significantly opened up. Some people don't pick up on it. When you have screens in here, you don't necessarily see it. In this case, you can see the gasket from the outside has also lost compression as well. So it's subtle. It's not huge, but it's there. And digging into it, I'm not going to get into like what is the type of black that's on here, but the reality is the sash is bowing, and we need to do something about it. And how do we fix it? And how do we address it? And how do we prevent it? And is this a conversation about durability? So here's where I get into this idea of durability being defined to, okay, air and water performance. Would this have an impact on the air and water performance of the building? Another very common issue is the main frame will start to bow in the corners and where mullions are. This is probably the number one that it gets initiated by homeowner comments because it looks unsightly. This one's quite extreme. This is in the Vancouver region as well. And it's basically, you've got almost a quarter inch, in some cases 3/8 of an inch of movement where this is pulling away. And from a building envelope perspective, when we deal with integration detailing and air and water tightness, this starts to become a concern. Is there any compromise of the seals of how this window was interfaced with the waterproofing and the air barriers of the systems? Those are the kind of questions we start to ask. You can see here someone's made an attempt to try to reseal this up to deal with the aesthetic aspect of it. And it's a real important part of this. There's certain, and I'll show some slides after, where there's dark materials that are exposed to heat, like metals that oil can. It's an aesthetic issue, but it's not necessarily a performance issue. Another situation I showed you the sort of chart where horizontal surfaces on south elevations become a bit of a problem. And this is one where we got a windowsill now, which has got a large horizontal surface. So it starts getting into the question about how is this sill attached? What's the structural attachment? Obviously, there's no nails through here. So it's assuming now that there's a back angle attachment on the inside, what can happen in this case is the inside, which is attached to a structural back angle, is structurally supported, but the outside is not. And so the outside is exposed to the heat, but the inside outside is exposed to the heat and the inside is not. So the window can actually start to droop down. And that's what we're seeing in this situation is the sill is drooping down right where there's basically a force, a weight acting on the frame, which is the fixed portion of this patio door. In this situation, we have a head retainer clip, a continuous head retainer clip, which is resisting the window or patio door, in this case, from moving in and out, but allowing the structure to move up and down without crushing the window. But the part where the sash is, you don't have any glass supporting it. We all know that the sash is typically undersized from the frame, so it's removable. And here you can see the sash sag as a result of being exposed to the temperature. This is one that's of huge concern to engineers and designers out there. These are two different buildings. They're both in the Lower Mainland. The one on the left is a vertical sash, sliding sash, and you can see here the gasket is not adhered to the frame. It's lost its adhesion. So there's a couple of things to look at here. Is gasket adhesion is one thing. Is why is it not adhered? And here's another project it's a different building. It's hard to spot on here because the gasket's black, but here's one where it was white in the same building. And you can see here we've got adhesion to the glass, but not to the frame, but we have adhesion to the frame, but not to the glass. And so you can see in this one, the window's got a bow to it. The glass is trying to stay straight. So now there's a force acting on the glazing. And in situations where the window has to meet guard load, and in this particular project, there's a concern now that none of the window, actually not a concern, there is a concern because calculations were done to determine whether or not these windows would currently meet guard load. They don't. So the piece of glass is 4 feet wide by 6 feet tall, and it's an occupied building. And if someone were to lean up against the glass, there's a high probability that the glass could potentially fall out of the frame because the glazing stop would not be considered structural. The glazing tape is actually acting as a structural adhesive from the glass to the frame. And this is a downward version of that vertical slider where the glazing tape's lost adhesion, and you can see the bow in the frame, and it's causing the glazing tape to pull off of the frame. joints that open up at mullions. This often gets reported as leaks by homeowners. And when we start looking into it, you start seeing gaps that open up due to mullions shrinking as well. These are large horizontal surfaces, and you can see the attempt to try to seal that up. And in this case, this project was done where a water test now was done after the fact. Windows are relatively older, but it's trying to determine whether or not that gap opening up is the cause of what's going on here. And you can see in this situation, on the inside, the gaps are tight, but on the outside, the gaps are open. So this is the same window, but you see the staining, the rust staining, which is an indicator that water's getting into the mullion where there's steel, there's causing corrosion, and then water's dripping out. And in this case, we drilled a hole in the underside of the mullion and water came pouring out. And this is the active leak occurring through the mullion during the actual water test. So this is where we start digging into the idea of, are these issues of durability and performance and the linkage between the two related? This one is, comment I get from a lot of people is this was old technology. Some of the black on these windows was the technology used, 5, 8, 10 years ago. This is a 3-year-old window. When I started talking about this conversation, a colleague of mine goes, "Yeah, I just bought a unit in a complex that I moved into in North Vancouver, and this is the windows that I have in my building, and the building's only 3 years old." So this is where we're starting to see certain situations now where product that has not gone through the heat dome and have been exposed to 40 degrees, it's still getting to a high temperature where it's causing this level of distortion. If you put your hand up against this, the amount of air leakage you're going to feel coming through on a -10 winter day is going to be quite excessive. So now you can kind of link the connection between excessive localized air leakage in cold climate with potential sash bow that's occurring from the summertime, and that sort of connection between the two. So what can change? Like, what do we need to do to address this? And where does the conversation need to go? Well, this is the Engineering and Geosciences of British Columbia, EGBC, we call it. This is the guidelines that are being put upon engineers. I'm not sure if the architectural industry has something similar, but it's basically a climate change action plan. So engineers have been instructed by their associations that they have to consider climate change into their building designs. They have no choice. It's part of their professional responsibility now moving forward. And there's sort of a chart here and all the different actions that they have to focus on, and sort of identifying a couple areas that are applicable to this issue as registrants. So engineers that are registered have access to high quality future climate data. So this is a big part of coming out of it, is the data charts we're using for climate generally are past historical events that we sort of gone through, and averages, and we have to start looking at potential, what are the future climate data that we're going to have to look at and design our buildings around, type of thing. So you can expect designers are going to start asking questions about durability, climate, different situations at hand. And common developers, like I would say government housing developers, for example, I know in British Columbia, a common trend would be, oh, if the water resistant rating per code, or the Canadian supplement, let's say, was 260 pascals, we are going to require 330, or a certain type of exposed building, we're going to require 510, because that is our way of defining more durable product that we want to put in our buildings. So you get government-owned housing projects that they're going to own these buildings long-term, ideally 50 years, provide low-income housing. They want that building to be durable because they're a long-term building owner. It makes sense. They have the right to do that. And if you don't like those projects, don't get involved in them, is what I've always said to people. But that's the reality. They're putting 10-story type of product on a 4 or 5-story building. But that is a test protocol that's done at occupancy. So there's a situation now at hand where you're seeing windows replaced in buildings within 3 to 4 years, but it passed those tests at occupancy. So is it a good durability test? And I kind of give this as foreshadowing to what we do in high rise in the world of PMU testing, where we expose product into certain types of tests. And then products and services requiring professional engineering scoped, basically getting into a managed climate risk. So you're going to start seeing designers focusing on how the products are going to manage the risk of climate change, and in particular, more extreme climate exposure that they're coming into. So this is coming in the world of design, and component suppliers, whether it's windows, siding, roofing, anything on the exterior of a building, are going to start being asked questions in regards to how are those products going to be able to withstand these. And if you've ever done work up and down like I've done from San Diego to Prince Rupert, is where I've worked in my career. And I can tell you what we do in San Diego is different than what we do in Prince Rupert. And it's just a reality of different climate exposure that we focus on. So are our standards good enough? This is the interesting part of our conversation. And so I look at the scope of NAFs, and then this is, if you've talked to me a bit, I kind of get on top of this topic of what is the scope of NAFs? Does it durability? And this is where you start looking at whether it's NAFs, whether it's NFRC, thermal aspects of things. Most of the standards in our industry are designed to create data that allows a consumer or a specifier to compare a product apples to apples for the most part at the point of manufacturing. And once it leaves the manufacturer's door, there's really not a standard that says, what is the durability life expectancy of this product? There's no standard that I've been able to find that basically will say this product has to meet those expectations for X amount of time. It's just left out in the open. It's like we tested occupancy, people move in, and everybody deals with the situation from that period of time. And whether it's done through a manufacturer's warranty, that's probably the only area that you would see a definition of durability. So start asking the question. Some people will start asking the question is what happens to your product when exposed to extreme temperatures? And what are those extreme temperatures and what are those boundaries? But does it address durability? And if we bring durability into the conversation, how would we do that? How do we deal with other dark materials on a building? Well, this is not an unknown issue. And you talk to designers and I say, if you're from Ontario, I think it's very popular to paint cabins in the Muskokas black. And, if you had a vinyl siding building that you bought and you decided to paint the vinyl siding black, what would happen, right? So we know black vinyl, dark vinyl siding. This is the effect of, this is metal roofing. This is the Okanagan of British Columbia, just a place I was staying at. And I'm like, oh, there we go. So there's it's an aesthetic issue, though. It's not necessarily a performance issue. So we know these issues exist. They're out there. We know how to deal with them to a certain extent. We know the limits. We know the boundaries. If I talk to an architect and I said, if you wanted dark siding on a building, what would you specify? Well, hardy or stucco. Not vinyl? No. Why would I specify vinyl siding? And so it's opening up that conversation. And I'm working with an architect on a project right now where literally they're in a situation with black windows. And I asked them, I said, how are you specifying black windows, as a color or as a material? And the architect's like, oh boy, okay, I see the issue here. Because we do it with siding, we do it with roofing. Where if we want a dark roof, we're going to specify, or a dark siding, we're going to specify the material that we use, not just the color. So to wrap this up a bit, how do we specify finishes? How do architects determine the finish of a building? Is it a color? Is it a material? Or is it a system? And I think this is starting to open up the conversation about durability, because if you're specifying a finish as a color, you're not talking about durability at all. And I would say that is the current state of our industry. We're specifying everything as a color. We have to start focusing on a material, or as a system, and get creative with what is that system. This is where we start talking about the next decade is upon us. We're going to start seeing extreme temperatures in the cold and in the hot. So what is the system that we're doing that is going to be able to manage? And this is where I go, how we fixed leaky condos in British Columbia. We didn't make buildings stop water from coming in. We said we're going to manage the water that comes in. We're going to expect buildings to leak, but we're going to drain it. We're going to increase the drying. We're going to flash it out, and we're going to address it. And it became a system, not just this is the material like a space shuttle that's going to stop every ounce of the environment from coming in, because we know that's absolutely impossible, especially from a cost perspective. So focus on this idea of a system. And so, when we get into color, like, how do we specify windows? Well, the color of a window is generally specified at the development permit stage. So when I talk to specifiers and I ask them, how are you determining the right product that you're specifying for the building that you're doing? And a lot of times they go, well, we depend on the window manufacturer to provide us with feedback on what their product can and can't do. And then I talked to a manufacturer. I said, how do you decide what product you want to sell for that certain building? They go, well, if an architect specifies it, we'll provide it, because we assume that it's going to meet their expectations for the building that they're doing. But what happens here is we're picking the color of the siding and the windows in particular at what we call the development permit application stage. How many window manufacturers do you think are brought into that conversation at this stage? This stage happens probably 3 to 5 years before a building is even considered for its functionality. and its materials and components. So the color's set. It's linked to the marketing and housing trends, of course, right? What's the biggest housing trend right now for bathrooms? Black faucets on everything. So what was it in the 80s? Probably gold. What was it, 20 years ago? Satin nickel. So housing trends are dictating a lot, but housing trends and marketing have no conversation about durability. Back in what we learned in the leaky condos is more money was spent on marketing condos than was spent on the conversation of envelope durability. And so that was something that was sort of a red flag that occurred in the industry that we have to be careful when these conversations come up. Thermal performance. So when do we determine the U value? Earlier on, I said it's commonly linked to zoning. Because the step code conversation happens very, very early when we decide what kind of building we're going to put on. We decide what step code we're going to build the building to, which determines the U value in the solar heat gain, which then determines the thermal conductivity, which then often determines the frame type. And so how often are you given an opportunity as a manufacturer to provide feedback to a designer on what's appropriate and what's not appropriate? And then budgeting. When a project is budgeted, it's typically the product is picked for a building. And I have a client I'm working with. I got called in on the project, and they had discovered about the combustibility changes in the code, where they could put non-combustible or combustible windows in a non-combustible building, and it's a 10-story building. And they just budgeted it based on vinyl, but it's right on the ocean, and it's exposed to about a PG 60 wind load. And my question was, okay, do we have a product that can work in vinyl? Do we have to have a bigger conversation about this? Because it wasn't just about combustibility from a durable perspective. It was about also the wind load that comes with the 10-story building, and we have to figure out what it is. So, these three steps, we find that we're not given enough opportunity to provide that consultation that is required at that time, when we can have influence as to what is the right product and the right system that is going to accomplish, at the end of the day, the reality. I do want to caveat this whole conversation. I have black windows in my house, and they work, but they're north facing. They're not direct facing to the sun. The windows that I have on the front are south facing, and they're white. So the important part is black windows can work, but they have to work in an environment that is suitable for the actual performance that goes into it. And so I use this term we. I'll wrap it up with that. Who is we? And when I speak to the entire audience on this conversation, we is everybody in this process. It's the designer, it's the specifier, it's engineers, it's architects, it's developers, it's builders, it's manufacturers, and it's also the consumer. It's everybody. And so everybody has an expectation for performance. There's nothing worse than putting a roof on your house and finding out 10 years later you have to replace it right away when you had an opportunity to put something on that could last 30 years and it had a slightly higher cost. So, the reality that comes in is we are going to be anticipating durability as a bigger conversation that comes into the threshold. So we have to open up these ideas and understand the boundaries, and then start developing systems and products that can accommodate these new environmental loads that we're exposing our buildings to. So, can we test for this? So in conversations I've had with some colleagues of mine where we do a lot of high-rise curtain wall, window wall projects, 20, 30 stories, products coming from all over the world, newly developed products. We have this thing called PMU testing in the commercial sector where, someone will spend $100,000 building a 2-story window wall system, and they'll bring it to a lab, and they'll do a whole gauntlet of tests, from environmental tests to thermal cycling, seismic tests, and then test before and after. So you can basically put a product through it. And interestingly enough, there's an AMA 1506 test that deals with the laboratory heat buildup effects on fenestration product. And it is literally identifying exactly what we're seeing in the industry of products that go through the issue. And so you have a situation where windows are tested at a 24 degree interior temperature. It's a 43 degree exterior temperature with an infrared lamp. And the result is to measure the amount of bow that occurs in the frame. And so one of the things we're looking at is a possible durability test would be an AMA 1506 test with a NAFS test, which allows you to combine the two together for you can basically put a product through a potential environment and then do a test after and see what impact it has on the overall performance. So this is something that is starting to be talked about at the engineering kind of level when it comes to selecting products for performance. So We're currently in discussion with National Resource Canada, Research Canada, and Fenestration Canada to start developing guidelines around durability. So this is something that's starting to heat up in conversation. And the idea here is to look at, in particular, carbon reduction. What happens with carbon reduction when it starts coming into our code, and how does that impact overall issues that we're starting to see? So that wraps it up. So I 1 minute over.
Anton, thank you very much. And thank you very much to everybody that attended. Obviously, we're at time, but we'll go ahead and extend this a little bit so that we can open it up for questions. Before we do, though, I do have a survey for this group so we can gather a little bit of feedback on how important durability is to you. As Anton mentioned, NRC and Fenestration Canada are at the beginning of some discussions about what we could be doing as far as supporting the industry around this topic. So, Lee, if you don't mind going ahead and putting the poll out. Answers for this will kind of help us guide next steps. So, thank you very much for everybody that participates. And I guess just two comments while we're working through this poll. Um, when it comes to embodied carbon, I know Anton mentioned at the beginning that this is something we probably should be taking a look at. He's absolutely right. In the 2030 code, we are in the process of evaluating whether or not components need to be judged and codified for embodied carbon targets. Um, it's hard for me to say whether or not we're going to see component embodied carbon for that cycle, which would really mean like 2032 for provincial adoption. But there is a good chance that we will see it then. So, in my view, that's kind of our timeline that we have to deal with that. And then another comment was present and future data. In the 2025 code, there will be present climate data that will be updated. That's going to have a pretty wide effect on how our various metrics are going to be applied. But yes, up until this updated 2025 code, if they continue the way that it was being managed, we were always dealing with previous data. So from 1987 to 2016 was kind of the block of information that we were pulling. Anyway, those are couple comments. Is there any questions from the group? It looks like there's two.
There's
Um,
also Gordon Fear who has his hand raised.
oh, perfect. Patrick, I'll answer you right after we hear from Gordon. Can you unmute Gordon Lee?
Oh, yeah, sure. I forgot we had to do that.
Can you hear me?
Yep, can hear loud and clear.
One of the questions that I have, if you take a look at, there was a survey done at the AIA presentation back in Orlando at the beginning of the year. And so what they did is they went ahead and interviewed the manufacturers of what's important to the architectural industry. And the manufacturers all said performance and, U values and this and that, and test results. And then they went to the architects and they questioned them. They said, no, it's sustainability. Performance is important, but it's sustainability. What is the difference when you're talking about durability and sustainability of what the architects? Is there a difference, or is it just the difference in language?
Do you want me to jump in on that? Because I've spent my whole career working with architects, all the way up and down, like I said, from San Diego to Prince Rupert. And I can tell you, the further south you go, the more I hate sort of diving into this, litigious the market gets. So anybody who's ever done work, Washington, Oregon, California, it gets worse the further south you go. So the term sustainability, it kind of gets linked into, is it performance? Is it durability? Is it reducing liability? Is it reducing risk? Bottom line, and I'm seeing Patrick's comments in here, will we start trying to make windows that last 100 years? I just had a meeting with a strata complex on a 25-story high-rise. They got, aluminum and glass windows from the 80s, and there's opposition in the building to replacing them. Some people want to replace them, some people don't. And somebody in the building asked, one of the owners said, well, how long would our windows last? And I go, well, it's glass and aluminum. It'll last forever. The question is how long are you willing to put up with inefficiency? So, in the 80s, that was the best technology. It's great. And then we started to see things shift. And so sustainability is a very difficult, I don't like the word. It's sort of the same thing as what is high performance. It lacks context. We have to focus on what are the needs and what is the right product for the right building for the right intended use. So if you're putting a window in a hospital, what's the life cycle of a hospital? 100 years, 200 years? What do we expect that building to last for? If we're putting a window in a one-story wood frame building on a 5-acre lot that probably 10 years from now is going to be rezoned multifamily, what is sustainability? So it's a misleading comment. I don't like it. And the way I would deal with an architect in that situation is, okay, what's your definition of sustainability? In some cases, they go, it's recycled material. I had a conversation with somebody about embodied carbon where they were wanting to put stones that came out of the excavation of the lot into the concrete foundation. What does that do for the structural ability or certain other aspects or water tightness of the concrete and that type of thing? So, we come from a world, in my background, I, dealt with a lot of the LEED certified buildings. There's a calculation formula, criteria, number system you can put to the calculation and determine outcomes. There's passive house, there's net zero, there's all these different paths to deal with these issues. At the end of the day, ask the fundamental question: what is the service life of this building? And are we going to put components into the building that have shorter service lives than the building? And the common answer to that is yes. So then the next question is, okay, what will we anticipate the frequency of change of that product be over the service life of the building? And can we incorporate it so that it's easily updated? So for example, I have a building that I'm looking at now is built in the late 80s, stucco right up to the window. The owners want to put new windows in, but the stucco's right up to the windows. So the cost of remediation of those windows is massive. It's doable, but if you just put a wood trim around it, would it be more sustainable for future retrofitting? So in my opinion, the most sustainable building that we have is a building that allows for components to be updated based on technology change that occurs over the lifespan of that building. Simply put, that is my simplest definition of sustainability. So you can put a 5-year product in. And I bought a house that the owner put a 10-year roof in. I just had to replace it. It was sold as a house with a new roof. Okay, great. It's a 10-year roof. Is it garbage? Was that sustainable? Well, I got to replace it without really having to do any other issues with it. So, but I think the important part of your comment is the difference of industry, of perspective, and that needs to be aligned better between manufacturer and specifier.
Yeah, and to add a little bit to that, one of the key issues that I see coming is that the embodied carbon, speaking a little bit to Patrick's comments on shouldn't greater durability be aligned with a better embodied carbon? If we were looking at a full life cycle analysis, absolutely, that those two should be interrelated. For the first steps into this conversation, much of it's focused on what's called A1 to A3, which is really going to be cradle to gate. So the materials to the moment that it's being ready to ship to site. So it's not actually looking at a full life cycle. It's looking at how much embodied carbon it took to go from that raw material to it's now ready to be shipped to site and installed in somebody's house. If we're only looking at it from that vantage point, the concept of sustainability is very different than what it would look like if you looked at the entire life cycle. And so some of those nuances have to be considered if we're going to have a legitimate conversation about sustainability. And I think that's a big portion for me on the importance of us getting involved in that durability conversation early is like the embodied carbon conversation is going to rotate around this. We are going to be dictated by those metrics. How we shape our industry into that and what places we want to shape our standards to and what we hold the codes accountable for are all going to be very much determined by the type of work we do now and for the next handful of years.
That helps.
Adding to Patrick's comment here in regards to, technology change. Something we don't have a conversation about, like sustainability, durability, is, I would say, most of the window retrofit industry today isn't about durability. It's about technology change. The advancement of low E coatings, the advancement of the PVC window market, for example, from 20, 30 years ago to where it is today, and durability and reinforcing and composites and materials. I suspect, like, we can't ignore the fact that decisions on renewals 20, 30 years from now, we can't predict. We know what those are going to be. Who would have predicted, in the 70s, some of the technology we have, or 60s, the technology we have today that can go into a product? And so who knows what we're going to see develop in R&D, and we're seeing all these different aspects of technology sort of on the forefront. And I've seen some cool situations in the past where there's sort of different synthetics mixed in with certain things to increase durability, and those are the kind of things that I think the industry needs to encourage. But it could mean a product installed today, the technology that could be advanced in the next decade could actually justify replacing it within 10 years because the technology is just that much better. So who knows what that cycle could look like based on what's upon us. So it's just something to keep in mind, I think, is that, the auto industry, people used to have cars for a long, long time, and now they cycle them through because technology changes quickly. So.
Well, we are a whopping 12 minutes over. Let's see. We've got one more open question. Um, Understood, Patrick. Yeah, more AI. That sounds like an answer. Um, but thank you all, and Anton, thank you very much for presenting on this, and for everybody that answered the polls. Uh, and we are nearing the end of the year, so I don't believe we have another tech talk on the way. Terry, do we have any more for 2025?
Yeah, there is one for December.
Yeah,
Okay.
December 10th, we're launching the size-specific thermal calculator. So you'll be seeing invites coming out for that fairly shortly.
Right. So December 10th, come take a look at the new size-specific calculator that is actually going to launch on our site. I know we've been tirelessly working in the background, Terry and the Leighton team. So yeah, come take a look. We're pretty excited about that. And yeah, till next time.